Hi guys, it's Ms. Griffin again. We're taking a look at Unit 9, Skill 4, where we are thinking about relationships between 2D and 3D shapes. So our essential question says, how can we relate 2D shapes to 3D shapes with cross-sections and revolutions? So the first thing we're going to talk about is the cross-section of a 3D shape. And it's defined here as an intersection of a solid and a plane. Now that might seem a little bit goofy, a solid being a 3D shape, and a plane being a 2D shape. A plane is just like a flat surface that goes vertically, horizontally. You can think of your piece of paper as being a plane. It's a 2D shape because it's flat. You can think of a cross-section as a very thin slice of the solid. So when I think of this, I think of slicing a brick of cheese. So if my brick of cheese starts out as a rectangular prism and I cut a slice of it, my slice is now in the shape of a rectangle, which you guys can see a couple of the slices here. Even if I cut it this way horizontally, the slice would still be a rectangle because that base is a rectangle. I also think of cheese just because I love cheese so much. Alright, so cheese gone, and now we're looking at real shapes here. It says, describe the 2D shape resulting from each cross-section below. So we're looking at the first one, and it looks like the 2D shape is here, and I'm cutting through a cone. And in this case, I'm cutting downwards through the cone, creating a 2D cross-section in the form of a triangle. If I could spell it right, that'd be really cool too. Triangle. The next one, we're starting with a rectangular prism, and I'm cutting parallel to the base, and the base happens to be in this shape. When I draw it upright, it looks like this, just like my brick of cheese. And so in this case, the cross section is a rectangle. Okay, then I'm looking at this next one to the right of that. I notice that it looks like this. It's again parallel to the base because the base is in that same shape, just a little bit bigger. So that shape is here, which is a triangle. Okay, the next one, we are cutting a rectangular prism along a diagonal. And I know it seems like this shape comes out to be a parallelogram just because it's like tilty, but this is in fact a rectangle. And I'm going to show you in just a minute why it's a rectangle by using some of the websites below. This next one, we are cutting a cone at a diagonal, and it's making this like half oval. Looks like this. This is called a truncated oval. The word truncated just means a cut oval. So some of these are a little bit weird, so I want to take you through these two interactive websites. One of them is by Shodor, and the other one is by GeoGebra. Both of them are fabulous. I don't think I prefer one over the other, but they do allow you to see the manipulation of vertical, horizontal, and diagonal cuts, because you can see here that we can cut vertically, horizontally, or diagonally. Okay, so I did try to pull up a web browser right here in the app that I'm using to record, but it didn't work, so I'm recording a video of my computer. So I'm sorry if it's shaky. I can't hold my hand very still with this huge iPad. But anyways, so I'm on the GeoGebra website, as you can see, and I'm looking at a rectangular prism. So here I have my block of cheese standing upright, and I slice through it horizontally. So I'm going to take a look and see what this is going to look like when I just kind of rotate my shape around. When I rotate, you can see that that slice, the orange piece, is a rectangle, just as we had predicted on our piece of paper before. When I slice parallel to the base, it's a rectangle. But what if I slice diagonally? That's the one I feel like you guys may not have believed me on. When I turn the slice to be diagonal, cut through my cheese diagonally like a weirdo, what shape is it? Is it a parallelogram or is it a rectangle like I told you? So when I turn it to show me just the orange, I can see clearly that it is in the shape of a rectangle. There are right angles here in these corners. This line here is just part of the prism. It just shows us the top of the prism, the corner. But you can see when I move this around, that diagonal slice is, in fact, a rectangle. I wasn't lying to you. Now I want to take a look at a triangular pyramid, because we did look at that a second ago. So this has a triangular base, and it comes up, the edges come up to make a point at the top. So when I slice parallel to the base, as you can see here, I am creating that orange figure in the middle, which is, in fact, a triangle. So when I turn it to look at the face, it's a triangle. But what if I turn this so that it's a vertical slice? Let's see if this will work. So I turn it upright to make it vertical, and lo and behold, it is a triangle. Now, it's not always a triangle, because if I have a rectangular pyramid, and I'm parallel to the base, notice that the base in this case is a rectangle, so that means its slice is going to be rectangular. If we look at a cylinder, I could have a circular slice when I go parallel to the base, or if I turn it vertically, it changes into a rectangle. I could also play around with this diagonally, so on and so forth. So there's different things that you guys can do with this GeoGebra website that I think would help you to understand cross-sections a little bit more if you're stuck. Okay, so take a look at that. So now on this next page, we're taking a look at the cross-sections of a sphere. And they give us an example of a standard basketball is shaped like a sphere. Draw a basketball with a vertical, angled, and horizontal slice. So we're going to draw our basketball first, and we're going to slice through this vertically first. So that means we want to cut a slice in this direction. Now that looks goofy, right? The shape that we are cutting out of it looks oval, but it's in fact a circle. If I cut horizontally, I'm cutting this shape out of it, and that again is a circle. If I cut diagonally, and I'm cutting this shape out of it, that again is a circle. So every cross-section of a sphere is a circle, and I've got a GeoGebra to show you. Okay, so we're taking a look again at GeoGebra, that cool website we were just looking at on the last page, and I'm looking at a sphere right now, and you can see this cross-section's kind of low, but it's a horizontal one. So when I turn my shape, I can see that it is in fact a circle. That orange figure is circular. Even if I move my cross-section up higher, it's still a circle. When I slice it vertically, right, through the circle up and down, and I turn my shape, it's, wow, still a circle, even if I adjust the height of it. Well, the height's not going to adjust, I guess, because it's vertical. What if I change it to be an angled slice? And I turn my figure. Oh my goodness, it's a circle. Okay, so every time you slice a sphere, it turns into a circle for the cross-section. Okay? Okay, so you're back with me. We're looking now at revolving a 2D shape to make a 3D shape. So it says another technique to find the volume of a solid is to rotate a cross-section, which we just learned about, around an axis, being like a line of some sort. Think about a revolving door and how it swings or rotates around the center, creating a cylindrical shape. So you start with a door, and it rotates, goes around and around and around on the top and the bottom, creating a cylinder. Okay, so we've got this example down here at the bottom, example 3. And it says, describe the 3D shape formed by rotating each figure around the line M and then sketch it. And then determine the volume of the shape given the dimensions on the rectangle. So in this first case, we've just got a rectangle. And it's like that door that we just saw in the previous example, where it's going to just rotate around this like hinge essentially forever and ever and ever, and the bottom rotates as well, forever and ever and ever. It's an endless cycle. And you can see that, as we're required to do, this door shape on the right-hand side gets rotated around to become on the left as well, and therefore it becomes a cylinder. So that's the first answer to this question. But then it says find the volume. And so in order to find the volume, we need a reference sheet. And I'll just be your handy dandy reference sheet right here. Pi r squared h. So we need a radius, and the radius, remember, goes from the center to the outside, which in this case is 6 centimeters. And then we also need a height. The height is listed as the right-hand side of this, essentially door here, but it can be anywhere as long as it's perpendicular to the base. So we know that the volume equals pi times our radius of 6, square that, and then times the height of 2. And we're going to get it in terms of pi first, and then we'll round afterwards. So right now, you should be thinking about what 6 squared times 2 is. So 6 squared times 2 is 72. Attach your pi. And now type that into the calculator so that we can round to the nearest tenth. And so when I'm going to round this, my 1 looks to the 9, so my volume overall is 226.2. Box it in, and then you're done. So example 3 is continued here, and it says describe this 3D shape formed and sketch it, and then determine the volume in terms of pi if dimensions are given. So notice that this says in terms of pi, unlike the last one that told us to round. So notice here that we've got this half of a circle. And if I rotate it around this line M, it's going to take the top and keep it right where it is, take the bottom, keep it right where it is, but this curved portion here will get rotated around and around and around and around, and eventually it turns itself into a shape that should be familiar to you called a sphere. Okay, take a look at this next one. We've got a triangle being rotated around line M. The top part that's on the line will stay right where it is. The bottom part on the line will stay right where it is. But this outside corner will essentially get reflected over here, and you can see that it would be, this edge would be rotated around and around and around and around. Just like a weird door that gets spun around and around and around. Okay, and then this, of course, would be connected. So that should also be a shape that's familiar to you called a cone. Now this one does have dimensions on it, so we need to calculate the volume. And again, I'll be your handy dandy volume reference sheet formula, table, whatever you want to call it. Volume equals 1/3 pi r squared h. Okay, so we've got 1/3 pi, that's the easy part because they stay the same, something squared, and then times our height. So our radius here, remember, goes from the center to the outside of the base of the circle. And so our radius is 6, and then the height is the height of this cone, which in this case is 5. So we've got 6 squared and 5 here. So I'm going to type this part into the calculator without the pi, the 1/3, and then the times 6 squared times 5. And that gives me volume equals 60, and then attach your pi. So volume is 60 pi. In this next example, example D from example 3 continued, is a quarter circle. This actually just recently showed up on the exam, and a lot of students messed it up for some reason. This quarter circle is only getting rotated around this line here. And so notice that these 2 points would stay in the same position, but this would rotate around, 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 and around, and around, and around, making you dizzy, and it looks like a bowl or a hemisphere. So if our hemisphere has a radius of 6, then we can find the volume of it. But remember that we have to first take a sphere formula, which is 4/3 pi r cubed, and cut it in half. So really this is 4/3 pi 6 cubed cut in half. Okay, go ahead and type that into your calculator. Find your answer in terms of pi, please. Pause the video while you do it. So you should be typing in the top part first and then hitting divided by 2 to find out that you have 144 pi. Wouldn't it be nice to have 144 pies? So yummy. All right, last example here is another Regents question. These questions come up all the time. There's at least one revolution and one cross-section on every test. A student has a rectangular postcard. Has anyone ever sent a postcard to somebody? Where you have to write their address on the right, put a stamp on it, and then write your message on the left. Aw, so sweet. Okay, so we have this rectangular postcard and we are folding it in half lengthwise. So once I fold it in half, then it kind of looks like this. And then it says that I'm rotating it continuously around the folded edge. So remember that I folded it in half along this edge here, but now I'm going to rotate it around that continuously. Forever and ever and ever, just because it's so much fun to rotate postcards forever and ever and ever around the folded edge, you know? So I'm asked what 3D dimensional object below is generated by this rotation, aka what's made. And you can see here that even though their picture doesn't make sense, it is this cylinder because I'm taking essentially a door and rotating it around that axis in the middle, like the revolving door we saw in the first example on this type of problem. All right, go work on your practice problems and then check your answers, and then go work on your CFU. Adios.